In this lecture, we'll learn about Minimax search. What is Minimax search? It's a technique to pick the best move in an adversarial two-player game. Why do we care? Because this is a big help when we're developing artificial intelligence in a turn-based game. Let's look at an example. This example comes from Data Structures for Game Programmers by Ron Penton. He uses rocks, but of course I'm using teddy bears. So the idea behind this game is that you never want to take the last teddy bear. On your turn, you are allowed to take any number of teddy bears from a single bin, and you have to take at least one teddy bear. So this tree is rooted at the configuration shown at the top with 2 teddy bears in the left bin and 1 teddy bear in the right, and it's player 1's turn. And the next level of the tree, and this is often called a ply, like in plywood, there are different layers of wood. This is a ply in the tree. So one step down is all the different configurations that could occur from player 1 taking their turn. So on the left side, we have player 1 taking 1 teddy bear from the left bin. In the middle, we have player 1 taking 2 teddy bears from the left bin. And on the right, we have player 1 taking 1 teddy bear from the right bin. So to generate our Minimax search tree, we're basically going through the different game configurations that occur as people take turns. Now it's player 2's turn, and on the left subtree, you can see player 2 can either take the teddy bear from the left bin or the teddy bear from the right bin. In the middle, the only thing player 2 can do is take the single teddy bear from the right bin, and that leads to player 2 losing because player 2 lost by taking the last teddy bear. On the right-hand side, player 2 has 2 choices. On the right-hand side, player 2 can be particularly stupid and take both teddy bears out of the left bin, thereby losing the game. Or they can take 1 teddy bear out of the left bin. And then on the next ply down, it's player 1's turn, and either they've won in that middle subtree or all the way on the right, or they have a configuration that only contains 1 teddy bear, so they're going to have to take that teddy bear, which leads to them losing the game. So this is the game tree for a complete play of Don't Take the Last Teddy. That's the new name, and that's the programming assignment for this module. You'll, of course, extend what we're doing here. But once we have the game tree, we need to help player 1 figure out what they should do for their turn. Now I've marked the game tree with Minimax scores. So at the very top, at the root of the tree, player 1 is the maximizing player. They want to get the highest score possible. So the way we're applying Minimax scores down on the leaf nodes of the tree is if player 1 lost, they get 0, and if player 2 lost, they get 1. So player 1 wants to make a move from the root that gives them the best chance of scoring 1. Player 2 on the next ply down is a minimizing player. They want to try to minimize the score that player 1 can achieve, so they'll make the worst move for player 1. And then the next ply down, player 1 takes their turn and they're trying to maximize their benefit, and so on. So that's why this is called a Minimax search, is because we're alternating between minimizing and maximizing, even though we start with a maximizing move. Even though I've marked the game tree all the way up to the root, we need to understand how that works. So assume that I have now marked all these leaf nodes with the appropriate scores. And we'll see in the next lecture that we implement this with recursion. So now we back out of the recursion on the maximizing apply just above those bottom leaf nodes. So here, as we back out of the recursion from player 1 lost, player 1 picks the maximum score in all its children. It only has 1 child, so it just has to pick 0. 0 happens to be both maximum and minimum, but it picks the best number. It also does this on the next subtree, and again, no choices. This one we're actually lucky. Player 1 is going to score a 1 at this ply of the tree. Here player 1 picks the maximum of all its one child, so it has to be 0. And here's another place where player 1 wins. So we're backing up out of the recursion from doing our minimax search, and we just did the max level. So now we need to do the min level. So the minimizing player is going to pick the lowest score of all its children. Now on this left subtree, they're both 0, so it picks 0. On this middle subtree, it only has one child, so it has to accept that score. And finally, we see an actual decision. So the children have scores of 0 and 1. And because we are on the minimizing ply, we pick the lowest score between 0 and 1. So we pick 0. Because remember, player 2 is trying to do whatever is worst for player 1. But now player 2 is done, this level of the recursion is done, and so we back up to the root, and player 1 will decide between these three children. One child has a score of 0, one child has a score of 1, and one child has a score of 0. So player 1, because that player is a maximizing player, picks the highest score of the children, and that's a 1, and that makes it clear that player 1's next move should be to take 2 teddy bears out of the left-hand bin. Don't lose sight in the mechanics of figuring out how all this works. Our end goal is to tell the root of the tree, what should you do? And of course, that means that this is great for AI, right? We're trying to help AI make decisions. But that's how the Minimax process works in this small example. To recap, in this lecture, we learned about Minimax search. In practice, we usually limit the depth of search that we perform because in most cases, the fan out, the branches out of a particular game state are so high that we can't go all the way to the end of the game. So what we do is we limit the depth of our search and we use something called a heuristic evaluation function to assign a score based on whatever criteria we come up with for a particular game configuration. Common, more advanced techniques like alpha-beta pruning and iterative deepening are built on top of Minimax search. So alpha-beta pruning is a technique that uses Minimax search, but when we start exploring a branch that has no possibility of being better than our current best solution, we just prune that branch and we don't explore it anymore. Iterative deepening is a technique where we perform Minimax search to one level and save that result, then perform Minimax search to 2 levels and save that result, and so on. And this is a really useful technique when we have time constraints on how long we can execute the search. So in our Peak Game Studios game Cat, we actually used iterative deepening because based on the selected difficulty, the AI could spend a certain amount of time looking for their next move. And if we used iterative deepening, which we did, we could actually always have some solution when time ran out, but we could keep looking for a better and better solution until time ran out.